Okay, so what I'm going to do is I'm just going to work some problems from section 2.8, page 185. Okay. Alright, so number 1, it says if V is the volume of a cube with edge length x, and the cube expands as time passes, find dv dt in terms of dx dt. Okay, that's what number 1 says on page 85. Alright, so it says that you've got a cube. Okay, so I'm not going to be really great at drawing. Excuse me. So suppose this is a cube. Okay, and you've got a so a cube, you know, it's going to be, of course, the same on all sides, and it says that it's every side is the length of x, and it says that the volume. Okay, it says that the volume is expanding as time passes, so you know that the volume is going to be just x cubed. And it says find dv dt in terms of dx dt. Well, to figure out what dv dt is, you need to differentiate this with respect to t. So that's going to be dv dt is equal not to only 3x squared. It's 3x squared times dx dt. Why? Because we're taking this derivative implicitly. We're differentiating this with respect to t. So that's why it's times dx dt. Okay? And so that's the answer. That's it. Let's do number 2. It says if A, that's 2 parts. Part A. It says if A is the area of a circle with radius r, yeah, it says if A is the area of a circle with radius r, and the circle expands as time passes, find dA dt in terms of dr dt. Okay, so that means that if we want to figure out what the derivative of this is, or if we want to figure out what dA dt is, then that means we need to differentiate this with respect to t. We're going to get dA dt is equal to pi times not just 2r, but 2r times dr dt. Okay, so that's part A. Part B says, suppose oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, so it says that the radius increases at a constant rate of 1 meter per second. So the radius is constantly changing at a rate of 1 meter per second. So that's a dr dt. Dr dt is going to be 1 meter per second. And then it says that it says how fast is the area of the spill increasing when the radius is 30. So at the moment that the radius is 30 meters, it asks how fast is the area changing, right? It says how fast is the area changing. So it asks you for dA dt. Well, you have to use part A. Part A, here's the formula that you're going to use. So dA dt is going to be 2 pi times r, which is 30, times dr dt, which they tell you is 1. So you just plug this in, and you're going to get, you're going to get 15 pi. That's dA dt. Okay. All right, number 3. Number 3 says each side of a square is increasing at a rate of 6 centimeters per second. So you've got a square, and every single side is increasing. So this side is getting longer, this side is getting longer, this side is getting longer, this side is getting longer. So, you know, this square is getting bigger and bigger and bigger. Okay. And so, so since it's getting larger, it says, each side of the square is increasing at a rate of 6 centimeters per second. Now, usually we call the side of a square S, you could call it. And so that means that area is going to be S squared. Okay? And then it says, we're told each side is increasing at a rate of 6 centimeters per second. So that means we're told a ds dt. It's 6 centimeters per second. Okay? And then it tells us at what rate is the area of the square increasing when the area is 16 centimeters squared. So what we're going to do is we're going to take the derivative with respect to time. We're going to get dA dt is equal to, the derivative of s squared is 2s times ds dt. Okay, so we're asked how fast at what rate is the area changing, or at what rate is the area increasing when the area of the square is 16 square meters. So it tells us that area is going to be 16 square centimeters. But we're asked to find dA dt. It says how fast is the area changing. So dA dt is what we're looking for. It's equal to what? Well, we have this formula that has a relationship with dA dt in it. ds dt we're given, so we can plug that in. But we don't have a number to put in for s. But we do know that a is equal to 16. Now, we know that a is equal to 16. We also know that a is equal to s squared. So that means that 16 must equal s squared. So if s squared is equal to 16, then that means s would equal plus or minus 4. But you can't have a square with a negative length, so it's got to be positive 4. So that means that positive 4 is going to go inside here. And so that means that dA dt is going to equal 2 times 4 times 6. So that's going to be 48, and that's going to be square centimeters per second. Okay, let's do number 4. It says that the length of a rectangle is increasing at a rate of 8 centimeters per second. Okay, so this is a rectangle. Okay, it tells us that the length, so we'll call this length, we'll call this width. It tells us that the length of the rectangle is increasing at a rate of 8 centimeters per second. Now that's a dL dt. It says it's increasing, so that's a positive number, and it says it's increasing at a rate of 8 centimeters per second, so that means it's going to be 8. Let me put that over here. Okay, and then it says the width is increasing at a rate of 3 centimeters per second. So that's dW dt is going to equal 3 centimeters per second. Okay, and then what does it say? It says here, when the length is 20, tells us that when length is 20 and width is 10, no wait, width is, 10 centimeters. It says how fast is the area of the rectangle increasing? So how fast is dA dt changing? So what is dA dt? Okay, well, we got to figure out a formula that's got L and W in it and A. We know one. Area is length times width. Okay, well, then that means that we need to differentiate this with respect to T. And notice, differentiating with respect to T, not L, not W, with respect to T. So that means the chain rule applies to both. Okay, so that means I'm going to have to take the derivative with respect to T on both sides. Okay, so the derivative of A with respect to T, that's dA dt. The derivative of L times W Well, that's a product rule. So that's the derivative of the first, which is dl dt, times w left alone, plus L left alone times the derivative of w with respect to t. And so that's just 1 times dw dt. Okay? And so now we have all this information, though. We know the number that gets plugged in here is 10. The number that gets plugged in here is 20. The number that gets plugged in here is 3. The number that gets plugged in here is 8. So we're good. dAdt is going to equal 80 plus 60, which is 140, and that's square centimeters per second. Okay, because this was in centimeters, and this is centimeters per second, and this is centimeters, and this is centimeters per second, and centimeters per second times centimeters is centimeters squared per second. And so you're adding centimeters squared per second and centimeters squared per second, which you better be doing the same unit, because you can't add two different quantities that have different units. That doesn't make any sense. And so then you get centimeters per squared, or centimeters squared, square centimeters per second. Okay, that's our answer. Okay, let's do number 5 now. Okay, it says a cylindrical tank with a radius of 5 meters is being filled with water at a rate of 3 cubic meters per minute. How fast is the height of the water increasing? Okay, this tells us it's a cylindrical tank, so that's good. Cylinder. For a second I was thinking it said conical tank, but it's not a cone, because then I was thinking, well, like, which is it, right side up, is it upside down? But it just says it's a cylinder. Okay, all right, so that's a cylinder. It's a tank. Okay, cool. And it says it's got a radius of 5. So it's got a radius of 5, and it's 5 meters, right? Yeah, 5 meters. And it says it's being filled with water at a rate of 3 cubic meters. 3 cubic meters per minute. So it's being filled with water at a rate of 3 cubic meters per minute. That sounds like a dVdt to me. It better be, because it's 3 cubic meters per minute. It's a volume change with respect to time. So dV dt, change of volume with respect to time, right? Okay, cool. Then it says, how fast is the height of the water increasing? Well, fortunately, if you notice, they don't say at the moment that it's, 2 meters deep or 3 meters deep. And the reason is because it doesn't matter what time it is, it's always going to be increasing at the same rate. It's not like the inverted cone problem. At the inverted cone problem, how fast it's increasing here, like if you dump just a little bit of liquid, it's going to maybe come up a lot. But if you dump a little bit more, it's not going to come up as much, because there's more surface area in the top. So that's different. This one, it's uniform because it's linear. Linear this way, it's cylindrical this way, or it's circular this way, but the point is this is a linear direction. No problem. So it asks us again, what was the question? How fast is the height changing? So it wants to know dH dt. dH dt is what? That's the question. Okay, well, what's the volume formula for a cylinder? Well, it's pi r squared for the area of a circle. And then that area, that circle, is multiplied by its height. So so we have pi r squared times h. Okay. All right. Now, here's the deal. We're not told any other information. We're just told, we are told the radius, though. The radius is 5. Okay. And it says, how fast is the height of the water increasing? Let me see. Okay. Let's see, are we told the got a radius of 5 meters. Okay. All right. Well, okay. Well, here's the deal. Think about this. The radius is not changing at all. Radius is a constant, you know. Radius is staying the same. So the radius is a constant. So let's see here. If I take the derivative of this thing with respect to t, then I'm going to get dv dt is equal to pi times. Now this is a product rule. Okay. But here's the thing. This is a constant. So, I mean, you could just take the derivative of it, but dRdt should be 0 because it's not changing. So you could take the derivative of this if you like, or you could, in this problem, see, this is kind of funny because r, we're told, is equal to 5. So that means I think you could just take this and plug this in for r now, and that would be sufficient. But if you didn't know that, and you took the derivative here, 2r times dRdt times h left alone plus r squared times 1 times dh dt. Okay, and then when you clean this thing up, if you for your height, like this term is going to just have to be 0. The reason that this term is going to have to be 0 is because dRdt is going to have to be 0 because the radius is not changing. Like, as you fill this thing up, you know, like, if you look, as it fills, the radius is always the same. Radius is always 5, 5, 5. Radius is always 5. It's constant. So that means that that term's just going to go away. So then what you really have is you have dv dt is equal to pi times, and you've got r squared times dh dt. Okay? And so then that means that r, we're told, is r is 5. So this is going to be pi times 5 squared times dh dt. And dh dt is what we're looking for, and dv dt we're told dv dt is 3. So we plug 3 here. Okay, so then that means now what we have to do is solve for this. So this is, we're going to divide both sides by 25 pi by 25 pi, and then dh dt is equal to 3 divided by 25 pi. Okay. And so that's what we get. Okay, so that's dh dt. Let's do number 6 here. Alright, number 6. It says that the radius of a sphere is increasing at a rate of 4 millimeters per second. So it tells us the radius is increasing. So that's dr dt. It tells us it's 4. It's increasing. It's positive 4. It says, how fast is the volume increasing when the diameter is 80? Alright, the formula for the volume of a sphere is 4/3 pi r cubed. Okay? So, if we take the derivative of this thing, then we get dv dt is equal to 4/3 pi times 3r squared times dr dt. Okay, and then dr dt, we plug this in here. Then we have an r. We're told that the diameter is 80. So that implies that the radius is 40. So then that means this, specifically this, is going to get plugged in there. So then we're good. So we get dv dt is equal to, we get 4/3 pi times the 3, so that's going to cancel, and then times the 40 squared times the 4 times drd. I think I worked this one earlier. And so this is 4 times 4, which is 16. So this is going to end up being 16 times pi times 1600. Okay, so just 16, so you got 32, 64, 128, 256. So this is going to be 256, 2 zeros, and a pi. pi. Yeah, that's what we get. Oh, and I'm sorry. This is in millimeters cubed. So cubic millimeters per second, I think it was, right? Millimeters per second, something like it's per second, right? Yeah. Sorry. Okay. Number 7. Okay, it says that the radius of a spherical ball is increasing. So radius is increasing at a rate of 2 centimeters per minute. So they tell us that the radius is increasing. So if they give you a rate, then that's a derivative. So the rate is increasing, so that means it's a positive number. So dr dt is equal to 2 centimeters per minute. Okay? And then they tell us at what rate is the surface area of the ball increasing. So dA dt, at what rate is the surface area of the ball increasing when the radius is equal to what? And then it tells us that the radius is equal to 8 centimeters. Okay? Alright, that's an interesting question. Alright, so the surface area. The volume formula for a sphere is 4/3 pi r squared. And I believe surface area, so area is equal to, and I think it's just like basically this derivative. So, or I'm sorry, 4/3 pi r cubed. That's the formula for volume. And I think it's just you take the derivative, so you get 4 pi r squared. If you take the derivative of this with respect to r, then I think the formula you get surface area. So I'm pretty sure the surface area formula for the surface area of a sphere. So we're just going to go with it. I mean, I'm pretty sure I remember seeing the 4 pi and stuff. So we're going to take the derivative with respect to t. We're going to get dA dt is equal to 4 pi times 2r times dr dt. Okay, so we're given the dr dt is 2, we're given that's 2, we're given this is 8, and then we're kind of done. So we get 8 times pi times 8 times 2. So this is 64 times 2 is 128, so 128 pi. And that's dA dt, which is like, what was the area in terms of, what number is it, 7? Yeah, this is going to be in square centimeters per, what is it, minute. Okay. So then let's look at number 8. Oh, this looks tricky. Alright, the area of a triangle with lengths of sides A and B, an angle, and contained angle A is, and they give us a formula. I think it's, yeah. So they say, suppose you have some triangle, and they say it's just any triangle, and so suppose it's triangle ABC. That means that this is side A, this is side B, this is side C. And they tell us that if you've got sides A and B and included angle theta, which is that one, then it turns out if you know this angle theta, so side angle side, if you know the angle between and you know those two sides, and that means that the area, so this is not side A, this is an uppercase A for area, it's going to equal 1/2 times A times B times the sine of the angle between them. Okay, great. Then for part A, this is a 2-parter, or 3-parter. It says if little a, is equal to 2 centimeters, and it says little b is equal to 3 centimeters, and theta. Okay, so these are fixed; they're not changing. And theta is increasing. So theta is changing, and theta increases at a rate of 0.2 radians per minute. So that means it tells us that d theta dt, 0.2 radians per second, or what is it? Radians per minute. Then it says how fast is the area increasing. So it wants to know dA dt. It says at the moment is equal to what when theta is equal to pi over 3 radians? Okay? Alright, well, it tells us the formula we're going to use. We're going to use this one. You know. So, we're going to differentiate this sucker with respect to t. So we're going to get dA dt is equal to 1/2 times. Okay, here's the deal. It's kind of like what we were talking about in that last example with this one, or I guess 2 examples ago, or I guess maybe it was 3 examples ago, where we told you that this was going to have to be 0 because the radius was a constant, right? So you really didn't need to do a product rule here. You could have just thrown a number in there. Excuse me. Here, A is a constant, B is a constant, because the sides of the triangle aren't changing. It's just the angle is changing. That's the only thing that's changing. So you could throw the numbers in there. You could say, okay, times 2 times 3 times the sine of theta, and let's do that before we take the derivative, basically, actually. So let's say A is going to equal, so the 2 and the half are going to go away, and so area is 3 times the sine of theta. Okay, cool. So now we can say, okay, what is the derivative with respect to t of this whole thing? Well, I'll take the derivative with respect to t of both sides. No problem. And so you're going to get dA dt is equal to 3 times, because that's a constant multiple. And then what's the derivative of the sine of theta with respect to t? The derivative of the sine of theta is going to be the cosine of theta times d theta dt. Don't forget the d theta dt part. So the d theta dt, they gave us something to plug in there. They said plug in 2 for that. They told us that theta is going to be pi over 3, so we know that. Okay, and then you get dA dt, so that's it. So dA dt is going to equal 3 times, right, the cosine, pi over 3 is 1/2. And d theta dt is 0.2, and that's like 2 over 10. And this is going to be in, this is going to be in like centimeters or something, square centimeters per, what was it, per minute? Okay. So these 2's will cancel, you get 3 over 10, so the answer is going to be 0.3 centimeters squared per minute, or square centimeters per minute. Okay, that's a juicy problem. That's pretty cool. Alright. Let's do B. B says if A is equal to 2 and B increases. So now in this situation, B is increasing. B is increasing at a rate of 1.5 centimeters per minute. So that means dB dt is equal to 1.5 centimeters per minute. And theta is increasing at a rate of 0.2 radians per minute. Then it says, how fast is the area increasing? When B is equal to 3 and 3 centimeters, and theta is equal to pi over 3 radians. That's what it's asking for. Okay, well, big surprise, we're going to use the same formula again. It was A is equal to 1/2 times A times B times the sine of the angle between them. Okay. Alright, so now here's the deal. A is a constant, so we can just plug that in for 2. So that means A is going to be 1/2 times 2 times B is a variable, though. B is changing, so it's going to be a variable. And then the sine of theta, that's going to hang out because theta is going to change as well. So the 2 and the half are going to go away. So we get B times the sine of theta. Alright, that means we're going to have a power rule here. Now we need to get the dt in here. So we're going to have to take the derivative of both sides, which means you get dA dt is equal to, and then this is a product rule. So take the derivative of the first one, that's dB dt, times the second one left alone, plus the first one left alone times the derivative of the second. It's cosine of theta times d theta dt. Okay, so now all we got to do is plug in all of our known stuff. B is 3, so 3 is going to go there. Theta is going to go there. And there. D theta dt is 0.2, that's going to go there. dB dt, they told us as well, dB dt is 1.5. Right, and then they told us that's going to go down there. So that's it. Okay, dB dt is 1.5. The sine of theta. Alright, so, the sine of pi over 3. The sine of pi over 3 is root 3 over 2. Now, also, you could just, 1.5, you could call that 3 halves. Let's just deal with everything in terms of fractions. Plus, okay, and then b we're told is 3. And the cosine of pi over 3 is a half. And then d theta dt was 0.2, so that's 2 over 10. Okay, so let's see here. We're going to get basically 3 root 3 over 4 plus, you cancel, and you're going to get 3 over 10. Okay, so this has 2 2's, this has a 2 and a 5. So this needs to have another 2, this needs to have a 5. 20 is going to be your LCD, so you're going to get 15 root 3 over 20 plus 6 over 20. So your answer is going to be 15 root 3 plus 6 all over 20. Now, you can pull a 3 out if you like, and you're going to get 3 times the quantity, 5 root 3 plus 2 all over 20, but you don't have to do this. I mean, you could just say that, that's fine. I won't even say it. And then, let's put units in here. Centimeters, so it's going to be square centimeters per minute. Okay. If you want to know an approximation, you just plug it in a calculator and you get an approximation. Okay, that's cool. Let's do another one. It says if A is increasing at a rate of 2.5, so now everything's changing. It says A is increasing at a rate of 2.5 centimeters per minute, so that means dA dt is equal to 2.5 centimeters per minute, and B is changing at a rate of 1.5 centimeters per minute, so that's 1.5 centimeters per minute. And then theta is increasing at a rate of, so d theta dt is 0.2 radians per minute. And then it says, how fast is the area changing? So we got to figure out what is dA dt is equal to what, when, and it's got to give us values. A is 2, B is 3, and these are in centimeters. 2 centimeters, 3 centimeters is B, and theta equals pi over 3 radians. Alright, well, the formula we're going to use is 1/2 AB times the sine of the angle between them. Okay, well, I mentioned this earlier today in class. What's the product rule for 3 functions? We said it turns out it's going to be f prime times g times h plus f times g prime times h plus f times g times h prime. That's what it ends up equaling. Okay, so that said, if you're going to take the derivative, oh, I'm sorry, let me show it. We'll take the derivative of both sides with respect to t. I'm going to get dA dt is equal to the half as a constant. It's going to come along for the ride. Then we got to differentiate these 3 things. So the derivative of A is dA dt times B times the sine of theta plus A times, and then the derivative of the B, so that's dB dt times the sine of theta, and then plus, then the A and the B, and then the derivative of the last one, which is the sine of theta. The derivative of the sine of theta is going to be the cosine of theta times d theta dt. The whole thing's got to get multiplied by half. That's why I opened parentheses here. People probably make that mistake. Alright, so now all we got to do is just plug in our stuff. What was everything again? The ADT was, what was it again? It was like 2.5. B is what? B was like what was B? It was 3. And then the sine of theta was, or theta was pi over 3. And then A was 2, I think. A is 2. Yeah. And then dB dt was 1.5. And then it takes as long to look up what those values are. D theta is 0.2. I think that's all, everything. Yeah. So that means that this is going to be 1/2 times 2.5 times 3 times the sine of pi over 3 is root 3 over 2. Plus, and then A is 2. dB dt is 1.5. Then the sine of pi over 3 is root 3 over 2. And then plus A is 2. And then B is 3. And then the cosine of theta, that's 1/2. And then times the, what was it? It was 0.2. I think that's it, you know. So let's see, 1/2 and the 2 is gone. This over 2 is gone. Okay. So then what are we going to get? We're going to get 2.5 is 5/2. Yeah. So it's 5/2 times 3 over 1 times root 3 over 2 plus, and we've got 3/2 because 1.5 is 3/2 times root 3 over 1 now because everything else canceled out, and then plus, then you've got 3 over 1 times 2 over 10, right? Because you could just call it a fifth, I guess. Okay, and then yeah, and then just compute this thing. So this is 15 root 3 over 4 plus 3 root 3 over 2 plus 3 over 5. So common denominator is 20. So that's going to give you 75, I think. Root 3 over 20 plus 30 root 3 over 20 plus 12 over 20. And then you got to multiply everything by 1/2, which is fine. So then that's going to really be 75 root 3 plus 30 root 3, that's 105 root 3, because those are like terms, plus 12, all over 20, but then you have to multiply by 1/2, so that's over 40. So that's it. Okay, that's cool. Neat. Okay, number 9. Kind of getting tired of these, to tell you the truth. Maybe I'll just sort of stop this for now. I'll try to work some more a little bit later. I got some other stuff I'll try to give you guys a little bit later, okay?